section 10.3, we are looking at arcs and chords. So if we'll just refresh what we know about a chord. A chord, remember, just has to have two endpoints on the circle. So I have created a chord, and then if I want to draw another chord, I've created a second chord, and I'm going to call these chords segment FG and segment JH. And remember that chords are segments. So a chord here, for example, would be F, G, and another chord would be J, H. Now, I also created arcs. So I have two arcs that have been created. I have arc FG, and I have arc JH. Now, if you notice, these arcs are not coming from, or they're not, they don't have endpoints that are directed from the central angle. So we have a theorem that talks about arcs and chords, and this is theorem 10.2. In theorem 10.2, it says, in the same circle or in congruent circles, so we can have one or two circles or more, two minor arcs are congruent. So these are minor arcs, they're less than 180. They are congruent if and only if their corresponding chords are congruent. So if we know that if FG is stated to be congruent to JH, then those corresponding arcs are also congruent. So if I specifically state that JH and FG are congruent, those chords, those segments, then arc FG is congruent to arc JH, based off of theorem 10.2. So in our first example, if I draw a circle, so in example 1, we have two chords, and I state that those chords have the name KL, so segment KL and segment JN. And you are told that JM is congruent to KL. So JM is congruent to KL. If I tell us that the measure of KL, so the measure of arc KL is equal to 90 degrees, and I want us to find the measure of arc JM. So the measure of arc KL is equal to 90 degrees. Remember, if the two chords are congruent, then their arcs are also congruent. So if KL is 90 degrees, so from K to L is 90 degrees, and segment KL was congruent to segment JM, then we know that arc JM is also 90 degrees. So if we look at another example of this, given a circle with two chords, chord AB and chord CD. If I tell you that AB, chord AB, is congruent to chord CD, so we know that the chord, remember a chord is a segment, is congruent to chord CD. Without knowing anything else, as long as you know that those segments are congruent, that the two chords are congruent, then we know that their arcs are also congruent. So that means that AB, arc AB, and when I'm talking about the arc, I am referring to this part of the circle, is congruent to arc CD. So AB would be congruent to CD, arc CD. if I tell us that arc AB is 60 degrees, then I can easily find the measure of CD. So the measure of arc CD is also 60 degrees, based off of the theorem that we looked at. Okay, so how can we use this in algebra? Well, the next example, we will see that. We're going to have two circles in this example. So two circles. Tell us that we have circle J and it is congruent to circle K, and MN, arc MN, is congruent to arc PQ. We are looking for the distance of PQ. So here's my arc MN and here's the arc PQ. So arc MN and arc PQ. And we have circle J and circle K. Now, in this problem, we're looking at some algebra. So I know that MN is 2x plus 1, and PQ is 3x minus 7. So now, if I tell us the converse of that theorem, if I say that MN, the arc MN, is congruent to the arc PQ, then we can easily find the distance or the length of MN or PQ. So if MN, arc MN, is congruent to arc PQ, then we know that segment MN is congruent to segment PQ. So this is the information that we need in order to solve for X and find PQ. So at this point, I know that they're congruent, so therefore their distances or their measurements are the same. They're equal by the definition of congruent segments. So 2x plus 1 is equal to 3x minus 7. So I solve that algebraically. I add 7, subtract 2x, and I get x is equal to 8. Now, it didn't ask me for x. It asked me for PQ. So to find PQ, I must plug back in 3 times 8 minus 7. So 3 times 8 is 24, minus 7 would be 17. So therefore, PQ is equal to 17. All right, the next concept, bisecting arcs and chords. Bisecting arcs and chords. It says if a line, segment, or ray divides an arc into two congruent arcs, then it bisects the arc. So if we look at theorem 10.3, if a diameter or radius of a circle is perpendicular to a chord, then it bisects the chord and the arc. So let's look at what that looks like. If we have a circle again, it says if you have a diameter or a radius. I'm just going to go ahead and show a diameter. So we have the diameter. I'm going to call this diameter AB. And my circle is circle C. If the diameter is perpendicular to a chord, so that means I need another chord in this figure. I already have one as the diameter, but I need another one. There's another chord, and I'm going to call that chord XY, intersecting at point Z. So if a diameter or radius, being that the radius could be CB, the diameter being AB, is perpendicular to a chord. So perpendicular, you will be told that that is forming the 90-degree angles when the diameter intersects the chord. Then it bisects the chord. So for instance, if I knew that chord XY was 100 degrees, then I could easily find XB. It's just half of that because this diameter is perpendicular to this chord. So it's bisecting the arc and the chord. So because if this diameter is perpendicular to this chord, then I know that XZ is congruent to ZY. So XZ would be congruent to ZY. And I also know that arc XB is congruent to arc BY. So let's talk about that one more time. If we have a diameter or a radius, AB or CB, it doesn't have to be the length of the whole diameter, and it's perpendicular to another chord XY, then that diameter bisects the chord and the arc. So if I know that XY is 30, then XZ is 15. If I know that XB is 20, then the whole thing would be 40. And BY would be 20 as well. Okay, we also have a theorem in 10.4. It says that the perpendicular bisector of a chord is a diameter of the circle. So what is that saying? It is letting us know that if we have this circle and it's the perpendicular bisector, then this is the diameter of the circle. So it's the length or across the entire circle. So let's look at an example of these before we move on. So in example 3, again, we have a circle, we have a diameter, and we have a chord. Remember, the diameter is a chord, it's just a special chord. And so we're given the diameter QS and we have the chord PR intersecting at T, and it is perpendicular. We're told that TR is 6, and we are looking for the arc of PQ. So it says that the measure of PQR is 98 degrees. So PQR is 98 degrees. They want us to find PQ. So we're looking for the measure of PQ. If we know the measure of PQR, it's 98 degrees. So from P all the way to R is 98 degrees. So every bit of this is 98 degrees from P all the way to R. Then to find PQ, because it's a perpendicular bisector, we just take 98 and divide it by 2. And that would be 49 degrees. So the measure of arc PQ is 49 degrees, and the measure of arc QR is 49 degrees. Okay, the next part of this example, I want us to find PR, segment PR. Remember that that perpendicular bisector, not only is it intersecting or bisecting the arc, it is also bisecting the chord. So if TR is 6, then PT also has to be what? It has to be 6. So then I can easily find the distance or the length of PR by just adding 6 and 6 together, or 6 times 2, and that answer would be 12. So 12 units would be PR. All right, last theorem. In theorem 10.5, of course, we have a circle. It says in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So I have a chord, I'm going to call that chord FG. I have a chord, I'm going to call that chord JH. So this is FG, and this is JH. And it says the two chords are congruent if and only if they are equidistant from the center. Well, equidistant means that they're the same measure from or to the center. So from this chord to the center has to be equal to this chord to this center. And it doesn't have to form a line, it just so happens to be the way I drew it. So actually, let me go ahead and move that arc just so it doesn't look like I'm making it be congruent. Okay, so they're equidistant. That means that they're the same measure, and then these form 90-degree angles. So in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So if I know that from the center, circle L, from the center L to the chord, if it's equidistant to both chords, then I can know that FG is congruent to JH. So FG is only congruent to JH if and only if LX and LY are equal. So LX has to be the same as LY. So if they're equidistant to the center, then the chords will be congruent. We have to be told that they are equidistant. So let's look at an example of this. This is example 5 in your textbook. We have a circle. We have two chords. That are equidistant from the center. And that's going to be stated. So this would have to be marked equidistant from the center. This is circle A, chord WX and XY, and they're being intersected at point C and point B. So I'm telling us that WX is equal to XY, which is 22. So WX and XY are congruent. So that lets me know that they have to be equidistant. BA has to be equidistant from AC. So WX is congruent to XY. That's why I know to go ahead and mark that these are congruent, equidistant to the center. We're looking for AB. So I need to give you some information. I'm telling us that AB is 5x and AC is 3x plus 4. So this would not have been marked congruent to start with. We know that it's equidistant because the two chords are already told to be congruent. So I know that AB is congruent to AC. So I can simply just say 5x is equal to 3x plus 4. So x is 2. It didn't ask for x. It said to find AB. So I take that and multiply 5 times 2 and I get 10. So therefore AB is 10 units. Okay, so I want you to work on page 718, problems 1 through 6. Problems 1 through 6. Stop the video, work the problems. When everyone is complete, press play, and I will discuss 1 through 6. Number 1, find x. Well, x is congruent to the arc ST. So we have this circle. We know the measure of ST. Remember that ST, the arc ST, is congruent to the measure of its central angle. Well, they told us that. It said that the central angle was 93 degrees. So therefore, arc ST is also 93 degrees. So they're wanting us to find x. Well, we have a chord, and then we have a chord over here, and they told us that these were congruent. So if they're congruent, then their arcs are also congruent. So this arc is 93, then RS is also 93. So therefore, arc RS or X is 93 degrees. And number 2, I have that the arcs are congruent. They tell me that this is 4 and this is 4. And then from F to H is 220 degrees. So to find FG and GH, I know that they're congruent because their chords were congruent. So these arcs are also congruent. So I can take the total sum of the circle, which is 360 degrees, subtract 220 from that, which is 140, but I'm being asked to find X. Well, X is down here, so that's only half of what's left, 140 degrees. So I take that 140, divide it by 2, so therefore, X degrees is 70 degrees. Okay, number 3. Number 3 was pretty easy. You just know that the chords are congruent, so the arcs are congruent. So 5x plus 3x plus 6, 5x is equal to 3x plus 6. So therefore, you find x to be 3. So number 3, x was 3. Okay, number 4, we have a circle, and we have a diameter of the circle, and we also have a chord, JK. Remember that a diameter is a chord, it's just a special chord. So JQ to QK, and then the diameter LM with center P. So in our textbook, they label PM to be a distance of 6. So if PM is a distance of 6, then I can also look at this and know that this forms a right angle because it's marked in our textbook. JK is 10, so the entire segment is 10. So half of it would be 5. And then JLK is 134. So JLK from here all the way to here is 134 degrees. So I have to find JL. So JL is real simple. It's just going to be half of 134, which is 67. But then at number 5, I had to find PQ. Well, PQ is the measure of this segment. So to find PQ, I have a right triangle. If I look at this, I'm going to draw or add a right triangle. I just created another radius. Well, the radius of the circle was from P to N. It was 6. So therefore, the radius there is also 6. The radius is constant. It's never going to change. So now I have a right triangle, and I can easily find QP, right? Using Pythagorean theorem. So I'm going to find PQ. I'm going to let that be A. So A squared plus 5 squared is equal to 6 squared. So A squared is equal to 36 minus 25. So A squared is equal to 11, or A is root 11. Because I'm looking for, it said to find PQ, all I had to do was find A. So therefore, PQ is equal to root 11, or it said to the nearest hundredth. So if it says to the nearest hundredth, that lets me know that I need a decimal form, and that answer is 3.32. So that would be number 5. Number 6, encircle J. GH is 9, KL is 4x plus 1. We know that they're equidistant. RJ is equidistant.